University, and you will be going to be Taiwan University for 10 weeks. He is our NTU Math Visiting Chair and also NCTS Distinguished Scholar. And Professor Simon is Australian Academy of Science, and also Fellow of Royal Society and Fellow for many other like AAS, ANS, and he got the Rory Steele Prize and the Buckner Memorial Prize, and it's very rare opportunity to give us this introduction course on geometric measure theory. The geometric measure theory is a very powerful tool and has been applied to many important problems. And Professor Liang Simon is the world leading expert in this field. Let's just welcome Professor Simon and leave all the time to him.
Thank you, Yng-Ing. That was a very generous introduction. So as Professor Lee said, geometric measure theory has proved to be really an important tool for anyone these days that works in either analysis or differential geometry or related fields. So it's good, I think, for anyone that intends to do research in those fields to have at least some introduction to that. So that's the aim of these lectures. Well, let's see. The most important reference for us at the moment is where you can find the text for the course. So that is currently on the Stanford website. That's the place to find the text. And I'm told that some of you will be taking this course for credit, so I need to propose some problems for you to work on if you want to take this course for credit. So I won't be giving you many problems, just a couple each week, just to try to help you to keep up with the material. So for the first week, I've just set two problems for the first week. Problems 1.1 and 1.5 at the end of chapter 1 of the text. And if you wish to have those graded, you should give them to me by Monday's lecture, next Monday's lecture. Let's see, yeah, it's the 5th today, is that right? So this is March the 12th. Yeah. Okay, so I know different people have different approaches to measure theory, and I'm sure that all of you have had some sort of course in measure theory before, but to make sure that we are approaching that in the same way, I think it's good to spend some time in the first lecture reviewing some of the basic results about measure theory. So I'm going to do that in the first lecture. So the first, the key concept here is the concept of outer measure. So X is going to be any space usually X will be a metric space. For the moment, it's just abstract. And the definition here is that mu is an outer measure on X. Outer measure on X. If mu is a mapping from the collection of all subsets of X into the non-negative extended real numbers, so 0, infinity. Notice infinity is included, so mu may take values plus infinity for some sets, with the properties that firstly, the empty set, of course, has to have measure 0. Second property is that if A is contained in B, these are any two subsets of X, then the measure of A should be less than or equal to the measure of B. This property is sometimes referred to as monotonicity. Monotone. Say that mu is monotone. And the third property is that it should be countably sub-additive. That is, that mu, so if you take a sequence, if they're all subsets of X, all subsets of X, then the measure of the union is less than or equal to the sum of the measures. By the way, notice there's no problem here about convergence. This may diverge, but if it diverges to infinity. So keep in mind, this side, of course, could be plus infinity. But that doesn't matter. It's still what you require. So this, in some cases, this inequality could simply say infinity is less than or equal to infinity. So that's the definition of outer measure, and of course that's foolishly general, so it's in itself it's not so interesting, but it gets interesting as pointed out by Carathéodory, the famous Italian mathematician, that you can identify certain measurable sets. Notice mu is defined on all subsets, but you can identify certain measurable sets, and so that's Carathéodory's definition. A subset A contained in X is mu measurable if mu of any other set S can be written as the sum mu S minus A plus mu S intersect A. Now, that looks sort of a bit funny at first, but you see what it's saying geometrically. It's saying that, here's a schematic picture of that. Here's S, and A maybe here is A. What it's saying, you see, is that the requirement on A, for A to be measurable, the requirement is that A has to cut S into two pieces additively with respect to the measure. Notice that's a nice way to say this, rather informally, actually. You can say that A is measurable if it cuts every other set additively. And notice this has got to hold for every S. Sounds like a lot to ask, right? Sounds very serious condition. And it's easy to construct measures where the only sets A that satisfy this are the empty set and the whole space. You can easily construct measures like that, but they're not interesting, those measures. Turns out this is the right definition, and Carathéodory realized that. So informally, you say this, that A cuts every set S additively. That's a nice way to say that. Like this picture. It says that the mu measure of that bit plus the mu measure of that bit must be equal to the mu measure of S. But that has to hold for every S. So it's a nice clear definition, but it's not clear if it's a good definition until you develop the theory, which we're going to do now. So first of all, a couple of remarks about this. I think I can do this right. So remarks. First remark is that notice it's always true that the empty set and the whole space trivially satisfy this condition. So the empty set and the whole space are always mu measurable. Second remark is that if mu A is equal to 0, then that also implies that A is mu measurable. So all sets of measure 0 are automatically measurable. Let's check that. Look at that definition there. In fact, let's look even more carefully at this definition for a minute. What's involved in checking this? That's a good question to ask. So first thing is to note that it's always true that the inequality that mu s is less than or equal to that right-hand side. That's always true. That's just the subadditivity property of the outer measure. That's this property when all of the, what happened to our, oh, here. That's this property when all of the AJs are equal to the empty set except for 2 of them, right? It's just that property. So you always get an inequality for 3. So to check this, it's sufficient to check that the reverse inequality holds, that mu S minus A plus mu S intersect A is less than or equal to mu S, because the reverse inequality is automatically true. So you only have to check an inequality. You don't have to check the identity. Not only that, you only have to check this when mu S is finite. That's convenient in practice. So you only have to check it when mu S is finite, because if mu S is infinite, this inequality trivially holds anyway. It's always true in that case. So you only have to check this inequality in this case. That's very convenient. So let's go back now to this claim here, that mu A equals 0 implies A is mu measurable. So we've got to check this inequality in case mu A is equal to 0. Well, if mu A is equal to 0, of course, this is also 0 by this monotonicity property, you see? So that means this term is 0, and then there's a trivial inequality. So there's nothing to check. So that's certainly correct. And I think that's the main things I wanted to mention about that. But you see, this doesn't yet show us that this is really a good definition yet, because it's not clear how it works out for important cases. For instance, does it give you the theory of Lebesgue measure, for example? Those sort of questions. So we really need to examine this a bit more. So let's do that. In order to do that, we need to introduce a concept. Let's see. this is a fairly wide room, so maybe I'll use just this left half of this board and the right half of that blackboard. It won't be too much of an angle then. Okay, so I've got to introduce a concept before we talk further about these outer measures. First, the concept I want to introduce is called the notion of sigma algebra. A collection script A of subsets of the space X is called a sigma algebra if there are three properties actually that have to be true. First is that the empty set and the whole space have to be in the collection. Second requirement is that if A is in the collection, then so is its complement. And the third requirement is that if you take a sequence in the collection, a whole sequence in the collection, then the union of all of those is also in the collection. That's the definition of sigma algebra. By the way, that comes from the fact that if you algebra means this would be true just for finitely many sets. You see, they call that an algebra. A sigma algebra means you can take a whole sequence and the union is still in the collection. So that's where that word sigma comes from. Okay, a couple of remarks about that. First remark is that notice that it's automatically true. Oh, by the way, I forgot one important thing. There was a third point here that's rather important about this definition. That is that if A is mu measurable, then the complement is automatically mu measurable. In fact, there's nothing to check because look at that definition up there. If you replace A by its complement, this becomes the complement and this becomes A because the complement of the complement is the set itself. So this just says the same thing. It's the same statement. So actually, this, of course, it's an equivalence because you can always go backwards, take the complement. So that's important here because it relates to this. As we'll see in a minute, it relates to this property of sigma algebras. So the first thing to observe is that if you take a sequence like this one, then in fact the intersection is also automatically, it's not part of the definition, but it's true that the intersection, so the definition, third part of the definition is that countable unions of sets in the sigma algebra are also in the sigma algebra, but it's also true that countable intersections are also automatically in the sigma algebra, as long as the individual sets are. And let's check that. Let's check that. So we want to look at the intersection. Okay, so that's the complement of the complement. So that's the complement, so that's just another way of writing the same set. But then we can use De Morgan's laws, that the complement of an intersection is the union of the individual complements. So this is x minus the union, j equals 1 to infinity x minus aj. And that does it, right? Because each of these sets are in the sigma algebra because by property number 2. And then the union is in the sigma algebra by property number 3. And then the complement, again, by property number 2, is also in the sigma algebra. So that does it. Okay, good. So that's and let's see what else. Oh yes, another important fact in general about these sigma algebras is that if you take any family of sigma algebras of subsets of the space X, then the intersection of the common elements of all of that collection is also a sigma algebra. So if you take a collection of sigma algebras, some indexing set alpha, it can be any indexing set, it doesn't matter what it is, it doesn't have to be countable or anything like that. If is a collection of sigma algebras, then the intersection let's call that A, is a sigma algebra also. And that's pretty clear, isn't it? You just got to follow the definition there, so I'll leave that one for you to check. Check the three properties. For example, notice that obviously the empty set and the whole space is in this because the empty set and the whole space are in every one of these by definition of sigma algebra, and so on. All right, so, this property actually is rather important because it means that there's always the smallest sigma algebra which contains a given collection of subsets of the space X. That's rather important. So there is a smallest sigma algebra that does that because you take the collection of all possible sigma algebras that contains the given collection. Then this says that the intersection of all those, which is obviously the smallest possible sigma algebra containing those, is indeed a sigma algebra. So a corollary. There exists a smallest, so given a collection, given any collection let's call it script U of subsets of X, there always exists a smallest sigma algebra. Of subsets of X which contains the given collection, which contains script U. It's rather important. And one extremely important case of that So one important special case. If X is a topological space, notice so far X has just been an abstract set. It doesn't have to be anything in particular. But if X is actually a topological space, so the notion of open set makes sense. So if X is a topological space, then there exists a smallest sigma algebra which contains all the open sets, all the open subsets of X. And by the way, notice that's the same as the smallest sigma algebra which contains all the closed subsets of X, because of this property that, notice this is of course an equivalence because the complement of the complement is the set itself. So this is of course an equivalence. So saying, but on the other hand, the complement of an open set is closed by definition. So it's the same as smallest sigma algebra, which contains all the closed sets. All the closed sets. And this is called the collection of Borel sets. This sigma algebra is the collection of Borel sets. Very important collection. So the Borel sets, in particular, the Borel sets include all countable intersections of open sets, and they include all countable unions of closed sets, but much more than that as well. Okay, so that's the notion of sigma algebra. Now let's get back to this this question about our whether or not we've got a good definition of whether or not our definition of measurable set is a good one. So the key theorem there is that so the key theorem is that mu any outer measure on X then the collection of all mu measurable subsets mu measurable subsets is a sigma algebra. In other words, it has these three properties. Well, we already checked this one, right? We already pointed out that the whole space and the empty set are always measurable, so that one doesn't require checking. We also checked this one. We pointed out that A being measurable is equivalent to complement being measurable. So all we have to do is check this one. And there's a few steps involved in that. So check. So 1 and 2 are trivial. Already checked. 3 requires a bit of effort, several steps. Let's do step 1. And that is if you take 2 measurable sets. then the claim is, this is a claim, the claim is that the union is mu measurable. That's not as strong as 3, of course, but at least it's a start, right? So let's check this. This is a bit tricky. This is one of Carathéodory's clever arguments. Now let's see. Remember what we have to do. We have to check an inequality, don't we? We have to check that if you take, for every s, we have to check that mu s intersect A1 union A2 plus mu s minus A1 union A2 is less than or equal to mu s. Then, of course, it'll be equal because the reverse inequality is always true. And we can assume this is finite. So for every s with mu s finite, we don't have to worry about mu s equals infinity because, as I said before, if mu s is infinity, this is already true, trivially. So we have to check that inequality. So the trick is, if you don't start in the right place, you get in a big mess here. I think you should start with this term to check this. So let's do that. So mu s minus A1 union A2. Okay, now this is De Morgan's laws again. This is S, it's the complement of a union. That's the same as the intersection of the individual complements, right? So this is exactly the same as mu S minus A1 intersect with S minus A2, or in other words, intersect with, take the intersection with the complement, so minus A2. So that's just De Morgan's laws. That's true. And now this gives us the hint about where to go. You can think of this as being a new S, right? In the definition. You can think of it as a new S in the definition of measurability. So we can just use the definition of measurability of A2. So according to the, we're going to use the definition of measurability of A2. So according to the definition of measurability of A2, this is the same as, now instead of S, we've got this, so that has to be a constant. It has to appear everywhere. So mu S minus A1 intersect A2. Mu S minus A1, that's it, nu S, minus the S minus A1 intersect A2. So that's just the definition of measurability of A2. And yeah, it's important to pick always the right thing. Otherwise, as I said, you get in a big mess. I've managed to get in a big mess many times. But what you do next is work on this one and use the definition of measurability of A1. So this is the same as mu S minus mu S intersect A1. Instead of S minus A1, it's S intersect A1, and we've still got this term. Okay, and let's see, hopefully this is working out. Notice I can write this. And then, okay, that's right. Now, by the subadditivity, this term inside the bracket is bigger than or equal to mu of the union of these two by subadditivity, but there's a minus sign, so that it's less than or equal to. So mu S minus mu S intersect A1 union S minus A1 intersect A2. Yeah. Okay. And right. And so this is right. Yeah. So this is supposed to be staring us in the face here. Right, so let's see, what are we trying to prove? Right, right. So this is, this set here is S intersect A1 union A2, notice. Because this already takes care of S intersect A1, so it doesn't matter that we've taken off A1 there. We're intersecting with A2. So it's exactly that. You can check that. So that's the same as that. And that's it. Just take this term and put it onto the left, and it's exactly this. So that's tricky. That's Carathéodory's argument. But it does work. So that's the first step, mu measurable. And of course, then the... Oh, yeah, by the way, there's some extra information that we get out of this too. There's an important additional conclusion that we need for the rest of the proof. The additional conclusion is that if A1 intersect A2 is empty, they're disjoint sets, then this is just mu S intersect A1 plus mu S intersect A2. It's exactly what it is. So it says that, and you look at all the other terms, they cancel out. So this says, this string of any identities and inequalities says that, that you get additivity. Mu S intersect A1 union A2 is the same as mu S intersect A1 plus mu S intersect A2. So that's an important additional consequence here. Yeah, I think that's right. I didn't quite explain that very well, but you see, you look at that term combined with the negative of this, by the measurability gives gives this. So I'll leave you to check that. I didn't cheat. That's really is correct. Okay, so these are tricky arguments, but they're all but they do work. And so that's an additional conclusion in step one. Now, step two is, of course, you can inductively go to any finite collection. Of course, you mustn't make the mistake of saying then it's true for countable sequences. That's a different thing entirely. But at least for finitely many, it's correct. So let's try that. So step two is just use induction. Induction on the number of sets. So if you've got finitely many, mu measurable, then the union, K equals 1 up to n, Aj is mu measurable. And now we want to deduce that, right, I always forget this part of the argument. Yeah. Yes. Okay. US. Right. So you get mu s equals mu s intersect the union. J equals 1 up to n aj plus mu s minus the union. J equals 1 up to n aj. So that's the definition of measurability. And yeah, so this is less than or equal to, by subadditivity, this is less than or equal to the sum, j equals 1 up to n of mu s intersect aj plus mu s minus union j equals 1. Well, let's see. This is, this term is, right. Didn't get that quite right. Okay. Anyway, if anyone sees the right argument, please let me know. I need all the help I can get just now. Yes?
You don't need to assume that they're disjoints.
No, not yet. Or maybe we do. There's some point in the argument where I do want to take disjoint sets. Yep, in fact, maybe that's right. Maybe that's what I'm getting screwed up here. So, right, yeah, I think you're right. Who suggested that? Very good, thank you. So let's assume for the moment that these are pairwise disjoint. AI intersect AJ equals the empty set for every I not equal to J. Okay, then this becomes an equality, you see, by induction from this extra fact here. And now we're in good shape because union j equals 1 up to n is contained in the union j equals 1 to infinity of aj. So let's actually take a whole sequence now. Measurable pairwise disjoint, every I not equal to j, there's disjoint. And then for each n, we would have this. And then this is a sum by this induction on this additional fact here. And then this is, let's see, this is bigger than or equal to. This guy is bigger than or equal to the complement of the union from j equals 1 to infinity, aj. Now, this is a clever, again, this is clever. This is Carathéodory. Notice that as n tends to infinity, this converges to the sum, to infinity. Keep in mind, you can always do that. It's very luxurious to have non-negative terms. No need to worry about convergence. Either this converges as n tends to infinity, or it diverges to infinity, but it's still correct, whatever. So this tends to sum j equals 1 to infinity mu s intersect aj plus this guy. And now by subadditivity, this is again bigger than or equal to mu of the union of these. You see, by subadditivity, this is bigger than or equal to mu s intersect union j equals 1 to infinity aj plus this. And that's exactly what we wanted to prove. So that shows that union j equals 1 to infinity aj is mu measurable. Very nice. So that works. And then we can now drop this condition, because notice that that if you take any A1, A2, etc., in mu measurable, whether they're disjoint or not, then you can always do the following trick, a very nice trick. You can define AJ tilde. Well, first of all, define A0, define an extra set, A0 to be the empty set. Just for notational convenience, you define A0 to be the empty set, and then you define AJ tilde to be the union I equals 0 up to j of define that to be AJ minus the union I equals 0 up to j minus 1 of AI. Now notice that by construction, these guys are pairwise disjoint, right? Because AJ doesn't intersect, by definition, any of the previous AIs. So AK tilde intersect AL tilde equals empty set for every K not equal to L. So that means we can apply this. But we've got to be careful about that. We mustn't fall into a trap here. In order to apply what we just proved, you've got to know that these sets now are mu measurable, right? But that's good, because we already know this one is mu measurable. That's the finite union. That was step 2, the first part of step 2. And the complement is okay. Remember, we showed that also. So that's good. That means that this is mu measurable. So indeed, you can apply that, and notice that also that the union k equals 1 to infinity of AK tilde is exactly the same as the union from j equals 1 to infinity of AJ. So that's mu measurable. So this is mu measurable. So that's the end of that proof. And by the way, notice we also gained the additional fact that if you stare at this for long enough, you'll see the additional fact that comes out here, sort of analogous to the additional fact that came out of the finite union case. The additional fact that we can read off from these inequalities here is that mu of S, that if A1, A2 are pairwise disjoint mu measurable, if they're pairwise disjoint and mu measurable, then mu of S is this mu of S intersect the union is additive. In other words, it can be written as the sum, j equals 1 to infinity mu S intersect AJ. So that's an additional fact that we get, as well as getting the measurability and proving that it's a sigma algebra. You get this additional fact. And by the way, notice that this additional fact does not require S to be measurable. That's sort of interesting. This additivity holds as long as the AIs are measurable and pairwise disjoint. Then you get this additivity property. Now let's see, we should take a break now. So let's take a break until just before 4:30, and then I'll continue on. I'm supposed to stop at 5:20, is that right? Yeah. Okay, let's take a break. I believe this is what you'd call moving at a glacial pace. meaning extremely slowly. I somehow need to speed up, I think, don't I? Yeah. Yes.
How do we know that this inequality holds for, since it's not subadditivity?
Okay. We proved that these were. This is a measurable. These are all. This is measurable.
Yes.
And part of the additional. See this additional conclusion here. By induction, that also holds for any number of unions, any fixed number.
Okay.
Yeah. So you can apply that instead of 2 sets. You can apply it to n sets. That's what we've done there. Yeah.
Thank you.
Yeah. But seriously, should I speed up or not? Because I don't know the students here. So
I think most of them are, well, I think the distribution
it's fairly broad, so maybe it's better to start slowly then.
Yes.
Yeah, okay.
But I think many of them did this warm-up reading course.
Okay, so they've seen some of this before?
Yes.
Yeah.
So I think it's good to
Okay.
be slow and begin
Yeah,
at least
okay.
not to frighten too many.
That was my idea. Yeah, right.
No, but it's also good. I mean, even an expert could be slowed down by some details.
Oh yeah, no, I think that's important, that they see you get stuck, but not stuck too much.
Right.
It's bad if you get stuck too much.
No, I think for most of us, I don't know, my experience about this is at the beginning you could go through all the major theory very slowly. You
Yes.
figure out all the details, but eventually you get lost. You don't know what you are.
Yeah, that's right, exactly. I get lost very easily myself, so I'm inclined to go slowly. Hello.
So to define measurable by cutting.
Cutting, yes, that's
I guess used for
Carathéodory.
improve. Is it useful in practical computation?
I'm not really sure, but certainly I think that's one of Carathéodory's brilliant ideas, to realize that you should define measurable sets in this way. Start with an outer measure and define measurable sets in this way. Very clever.
So for example, in the topological space or even metric space, do we have a even more convenient computational definition? Some kind of approximation?
Not really. I think it's, unless you go to specific measures, yes, then of course a specific measure will be defined very specifically. But in this abstraction, I think that's it.
Thank you very much.
Right.
So there is there are 3 organic stores nearby.
Oh, thank you. Right. It seems that there are lots of interesting cafes, restaurants, and stores in this area. It's very nice.
I want to try, but this is kind of your map is not very.
That's fine. I've got my Google
Maybe sometime
Maps.
I will.
I've
I will
got
show
my.
you.
I've
It's
got
not
my.
it's not that far away. I will
Okay,
just go
great,
there with you.
great.
Maybe let me see. I'm teaching. Maybe tomorrow after my class. Maybe say
What time?
5 o'clock. Would
Oh,
that be
yeah.
okay?
Be fine. Yeah.
And then I just take you there. It's probably easier, and you can show it. So
Yep.
so the whole. So it's just within maybe 5 minutes walk.
Yep, yep.
There are 3 organic
Right in there.
store right
Okay,
there. And
that's
so
great.
this is your apartment here.
Yep.
So this is like we are somewhere here.
Right.
So this is like
We're here, aren't we?
Exactly.
Yeah,
So this
yeah.
is like 10 minutes walk
Yeah,
also.
yeah.
So it's not far away.
Oh,
So-
good. Great,
So they
great.
also have
Okay.
organic milk and.
Okay. So shall I come to your office then?
No, I just go to your place.
Okay,
Yes,
right.
I wish. And then
Right.
I think probably easier.
Okay,
I
so-
just show you there. And then,
Okay,
and
we
then-
can meet at 5
And then, so this is. I just tell you. At least you have some idea. So this is your tree, right? This is
Yes.
going to
Yep,
go
yep,
this way.
yep,
Basically,
got you.
it's going
Yep.
all the way, but somewhere you need to take
right,
a left turn.
okay,
so
okay.
it's quite easier. So,
Okay, great.
Yeah. So and. Because you mentioned you were vegan, so I
Oh, right.
and then you guys know like some people just
Right.
have organic, so they have some kind of organic store. You can buy vegetable
Terrific.
over there,
Right,
and then
right.
I mean the department store has organic, but it's a bit far away from here.
Oh,
right? And
yeah,
then also,
yeah. I noticed there are a couple of nearby department stores, but vegetable stores, but they don't have very much.
Yeah. Exactly. And so here they have. I mean they have. It's a small organic store, but there are 3 of them, so you can see which
Right,
one has more,
okay,
more
great.
options. And,
Thank you. You're
and
very
also you can
kind.
buy like
Yeah.
tofu or those kind of things.
Right.
So, yeah.
Need more water?
Yeah, if possible.
Sure.
You saved me. I was starting to have trouble. Thank you.
Yeah, I guess Yng-Ing probably has told you we sort of run some warm-up seminar for your class over the
Oh, yeah, okay, good.
So
right.
I guess
yeah,
most students
okay, so this
are
might...
prepared. So we,
Right, okay, good.
But it's okay. I think it's
Yeah.
good to have this.
Yeah.
As a,
No, I like to start off
I
slowly.
forgot all my major 3. I took this at
Right. I constantly forget all my measure theory.
when you learn measure, it's very technical, but then you use it and then forget all the detail how to put it. But I think it's good that you.
Right, but the nice thing about forgetting it is the second and third time that you have to relearn it, it's much easier, right, than the first time. Thank you.
Welcome.
I'm probably going a bit too slow, but that's
I
okay.
think it's good.
Just to warm up.
Yeah,
it's
just
a
to
good
warm
warm-up,
up.
I
Yeah, yep.
So probably if you use the microphone, will that help?
Okay, it might. Yeah,
Yeah, then you don't need to.
yeah, might
The
help.
microphone is pretty good, so maybe you can try it.
Right. But I have no.
我不晓得他要用哪一个。
Maybe you can
You
fit it
just,
here
yeah,
somewhere.
exactly. No, just
Yeah.
this is
Yeah, okay.
somewhere.
There, in this.
Yeah, then maybe
area.
like this way,
Or maybe it can. Yeah, that's
This
good.
way.
That's good.
and then just turn this on.
Right.
And then you can put this in the
In my pocket.
your pocket.
Yeah. Okay. Yep.
You can try the balls.
1, 2, 3. Yeah.
This one. Then you don't move.
Yeah. Great. Thank you. Oh.
You don't need anything.
No, nothing. Yeah. Thank you. Okay. So we proved that the mu measurable sets then form a sigma algebra. Now, one corollary that's important of that about that, and that is if you take A1, A2, etc. sequence mu measurable and AJ contained in AJ plus 1. So it's an increasing sequence of mu measurable subsets. Then mu of the union is equal to the limit of, as n tends to infinity, of mu an. Notice that there's no question that whether or not this exists. It has to exist because this implies that mu aj less than or equal to mu aj plus 1. So this is an increasing sequence of non-negative numbers. Of course, always keep in mind that both sides here could be plus infinity, but that's fine. And let's check this. Right. So mu, yes. Right. I think we need to do this thing again that we did a minute ago, aj tilde. So let A0 equals the empty set and aj tilde should be equal to, oh, right, no, that's not right. Let's see, right. Mm-hmm. Oh, yeah. So, yes, right. So, okay, yeah, stupid. Yeah, so let's do this. So this is mu. So let's let aj, let's let A0 equals the empty set, and then aj tilde is just aj minus 1 for j bigger than or equal to 1. That's actually similar to the thing we did before, but now we've got an increasing sequence, so we just have to subtract off the previous one, too. And then, yes, so then union, so mu union j equals 1 to infinity aj, as we said before, is the same as the union. This has got the same union. J equals 1 to infinity aj tilde. And that's by additivity. Remember, these are all measurable, so you can use additivity. So sum j equals 1 to infinity mu a. Oh, better to do this. Oh no, that's okay. Yep, aj tilde by additivity. And then this is the same as the limit as n tends to infinity of the sum j equals 1 up to n mu aj tilde. And now mu aj tilde is the same as mu aj. Let's see. Better not to do that. This is yeah. So I always seem to get this messed up. So so far we're okay. This is the limit of this. And now notice this finite sum is the measure of the union. These are pairwise disjoint, so it's the measure of the union up to n. So the limit as n tends to infinity, mu union j equals 1 up to n a j tilde. Now the union j equals 1 up to n of a j tilde is exactly just a n. Cancels out as you take the union. So this is the limit as n tends to infinity of mu an. So that's it. So indeed, this is correct. So that's a nice corollary. And a second corollary is that if you take a decreasing sequence, measurable sets with aj plus 1 contained in aj. So now it's decreasing rather than increasing. And one additional fact, you've got to assume that, and there exists some J0 with mu, and assume there exists some J0 with mu aj0 finite. Then you get the corresponding result to this for the intersection. Then mu intersection j equals 1 to infinity. Aj is the limit of mu aj, mu an. But notice this is false without this hypothesis. This is false without this finiteness condition. The classic example of that is to take aj, take the measure mu to be just Lebesgue one-dimensional measure on the real line. Lebesgue measure on the real line. And take aj to be the interval from j to infinity. Then notice that in that case the intersection is empty. So this side would be 0, but this side is plus infinity for each. This has got infinite Lebesgue measure for each j. So this is certainly false without this condition. And I'll leave that as an exercise for you to check. You simply apply this result to the complement. Apply this corollary, corollary 1, this first one here, with aj tilde equals aj0 minus the intersection j equals k equals j to infinity ak. So just apply the corollary to part 1. That does it. Okay, so there are a couple of important corollaries. And I think that's as much as we need to say for the moment about Carathéodory's definition. So that's Carathéodory's idea. That's how he did it. He took an arbitrary outer measure and defined the notion of measurable set, saying that it's measurable if it cuts every other set additively. And then he developed this theory that the measurable sets form a sigma algebra, and you have these corollaries, and so on. So now let's move on to slightly more advanced things. So first thing I want to mention is Egorov's theorem, which is a very nice theorem, and it makes use of this this result here. So Egorov. So suppose that mu is any outer measure on a space X, and let's see, I forget if we have to assume finiteness here. I think we do. Yeah, and yes. A mu measurable subset with finite measure And you've got let's suppose we've got a sequence of functions. Into the reals, k equals 1, 2, etc. And so let's suppose these are mu measurable functions. Remember, that just means the pre-image of any mu measurable function means that f is mu measurable. Means that simply the pre-image of any set of the form, any interval of the form alpha infinity. So you look at intervals, set of points bigger than alpha, and you take the pre-image of that. And that should be mu measurable subset. And so take such a sequence of mu measurable functions, and suppose that limit as k tends to infinity of fkx equals 0 for every x in A. Then, for every epsilon positive, you can find a subset B of A which chews up all of the measure of A except possibly for an amount epsilon. So there exists a mu measurable subset B contained in A with mu A minus B less than epsilon, and this convergence is uniform on B. Uniformly for x in B. That's a very nice result. It says that even if you've only got pointwise convergence, as long as you're willing to throw away a set of measures, a small set of small measure, then you get uniform convergence on what's left. That's very useful, and we'll see. We are going to make use of that in the more advanced material that we discuss later. So let's give the proof of this. It's a consequence of this monotonicity thing here. So proof. Well, the trick is to look at the right sets to apply this result to. So we want to apply this result, and the trick is to apply it to the right subsets. So you notice that if x is in A, then by definition of limit, we're given that the limit of fkx is 0. So by definition, that means that for every j, it means that x is in, let's call this set BJL. I'm going to define what this is. It's the set of x in A such that mod fkx, yes, too many x's, such that fkx is less than 1 over j for every k bigger than or equal to L. And I claim that this is true as long as you take L large enough for some L. In fact, that's clear, isn't it? Because this tends to 0. So eventually it'll be less than 1 over j for all k sufficiently large, bigger than or equal to L, for sufficiently large L. So that's just the epsilon delta definition of limit. So we can say that, but see, this is for every y in A. So that means that the union, this is true for some L. So So that means that A is actually the union. L equals 1 to infinity of BJL. What that statement says. Every point is in one of these BJLs. So the whole set is the union of these BJLs. And that's true for every J, equals 1, 2, etc. And by the way, notice that these are also increasing. If we fix J, BJL plus 1, notice trivially contains BJL. Because if it's less than 1 over J for every K bigger than or equal to L, then it's certainly less than 1 over J for every K bigger than or equal to L plus 1. So that's true. So that means we can use this monotonicity on these sets BJL. So that means that mu A equals the limit as L tends to infinity. This by definition is this. 1 to infinity, so BJL. So this is the limit as L tends to infinity of mu BJL. And that's true for every J. It's 1, 2, etc. Okay, so that means that we can make, by picking L large enough, we can make the difference between A and the subset BJL as small as we like. So for every epsilon, so we can pick, so let epsilon be given. That means we can pick an L large enough by this limit. L large enough, let's call it L sub J. It depends on J, of course, because this is just true for each fixed J. So it depends on J. So the sum Lj such that mu A minus Bj Lj is less than epsilon times 2 to the minus j. You can make it less than anything you like. But in particular, we can make it less than epsilon times 2 to the minus j. Since it actually has a limit 0 as L tends to infinity. So we can certainly do that. And then by De Morgan's laws, that's the same as saying that that implies, at least, that mu minus the intersection j equals 1 to infinity Bj Lj is less than the sum. Notice that by De Morgan's laws, A minus the intersection is the same as the union of the separate complements. That's these. And that means we've got a sum, j equals 1 to infinity, by subadditivity. So this is less than epsilon times the sum, j equals 1 to infinity, 2 to the minus j, which of course is equal to epsilon. So we have that. And this is going to be our set B. That's going to be our set B in the statement here. We're claiming that there's some set B with that less than epsilon. We've done that. We've got a set B with mu A minus B less than epsilon. What we have to do now is check that you've got uniform convergence in this. But you see, if x is in if x is in B, that's this set. If x is in B, then x is in Bj Lj for every j, right? B is the intersection of these. So, and that implies, by definition, that fkx, absolute fkx, is less than 1 over j for every k bigger than or equal to Lj. And that's for every, where for j equals 1, 2, etc. That's true for j equals 1, 2, etc. Now that's uniform convergence. You can make fk uniformly small for every x in B. You have this for every k bigger than or equal to Lj. Notice the k does not depend on the x, it's just bigger than Lj. So that's it. So that's Egorov's theorem. Nice theorem, and we will make use of that later in an important way. Okay. Egorov. Right. Okay, so now we still haven't quite convinced ourselves that this is really a good definition. Does it typically, this idea of Carathéodory's defining the measurable sets in the way we've defined them here, does it really lead to interesting measures and powerful measures with lots of measurable sets? And there's a theorem of Carathéodory himself that guarantees that that really works in a very nice general setting. So I want to explain that. It's Carathéodory's theorem. It's a theorem in metric spaces. Well, before I do that, I'd better give the preliminary notation, though. So remember, we've got the notion of the Borel sets now. If you take a topological space, you can take the smallest sigma algebra that contains all the open sets. That's called the Borel sets. It's a big class of sets, typically. And so X topological space. And the definition is that an outer measure mu on X is Borel regular. Borel regular if two things are true. First, all the Borel sets should be mu measurable. Now notice that doesn't mean there mightn't be more sets other than the Borel sets. In fact, often that's the case. But at least the Borel sets should be mu measurable. And the second requirement is that for every set A contained in the space, there exists a Borel set. B which contains A and which has the same measure. That's the definition of Borel regular measure, Borel regular outer measure. Now, be careful, there's a favorite mistake of people that are starting out in measure theory. The favorite mistake is to think that this implies, it doesn't, in fact it certainly does not imply in general that mu b minus a is equal to 0. That's a much stronger statement. And let's see what would you need to go from here to here? Well, if A were measurable, so note, there is a case when this is true, but let's talk about that. If A is measurable, then you would get that mu that mu b equals mu b minus a plus mu b intersect a. That's the definition of measurability. In fact, that would be true for every set S, not just for this set B, but in particular it's true for this set B. And but mu b intersect A, of course, is the same as A, right? Because B contains A. There it is here. B contains A. So this is just A. So this is mu b minus A plus mu A. So that tells you that mu b minus A is equal to mu b minus mu A, provided mu A is finite. See, you've got to be extremely careful about doing arithmetic when you're using measure theory, because keep in mind that both sides of this identity could be plus infinity. So you can't just subtract off mu a. Infinity minus infinity doesn't make any sense. So provided, this is correct, provided mu a is less than infinity. So yeah, you need, in order to say this is okay, this is okay provided a is mu measurable and mu a finite. There are two conditions before you can say that. So in general you can't do that. So you've got to keep that in mind, but only in this case in general can you do that. So that's the definition of Borel regular. And for people that have come to measure theory from a more abstract point of view, you often talk about a Borel measure as distinct from a Borel outer measure. You often talk about a Borel measure on a topological, on the collection, on a topological space X, a Borel measure. Now I want to show you that there's a close relation between a Borel regular outer measure and a Borel regular and a Borel measure on a topological space. So let's compare. So here we've got Borel regular outer measure. And here we've got a Borel measure on X. That just means, let's call it mu 0. Let's call this one mu. Mu and mu 0. So remember, Borel measure means that mu 0 is a mapping from the collection of Borel sets to the extended real numbers, non-negative real numbers, with mu 0 of the empty set equals 0, and with mu of a countable union of disjoint Borel sets Bj. So it's countably additive if Bi intersect Bj is empty for every I not equal to j, and Bj Borel for each I. So that's the definition of a Borel measure. Now what's the relation between that and Borel regular? Well, they're very closely related. If you've got one of these guys, you can come, so you've got a mu 0, you can come back and get a mu, one of these guys, just simply by making a definition. You can define an outer measure, mu. Now this is an outer measure. Now remember, that means that mu is defined on all sets, not just on the Borel sets, defined on all sets. And you can define an outer measure, a Borel regular outer measure, a Borel regular outer measure simply by taking mu, you take any set A and you define mu of A to be the infimum of the set of mu 0b, such that B contains A and B is Borel. Now we're getting a bit short of time, so I won't give the proof of that, but it's very easy, just a couple of lines. You can check that does indeed give you this is indeed a correct statement. You do get it. This is if you make this definition, it really is a Borel regular outer measure. It has these two properties. And furthermore, it agrees with the original mu on the Borel sets. Mu 0 equals mu 0 B for every Borel set. So going that way is okay. You can always get a corresponding Borel regular outer measure. And of course, coming back this way, if you start off with mu, coming back this way is trivial. You just take the restriction. You simply restrict to the collection of Borel sets. And that gives you such a measure. So that's rather nice. So there's no, you needn't be worried if you've learned measure theory from a more abstract point of view, talking about Borel measures. This is very clear. There's no real difference between Borel measures and Borel regular outer measures. It's just that Borel regular outer measures are usually more convenient to deal with. That's all. All right. So that's good. Now let's go to Carathéodory's theorem. It's really a nice theorem, and it sort of justifies his approach, I think, to a great extent. So here X is a metric space. Most of the time, this is all abstract today, but most of the time from now on we'll be talking about metric spaces, often in Rn actually, but at least in a metric space anyway. So any metric space and mu any Borel regular. Oh, sorry, that's the whole point. We don't know that yet. Mu any outer measure on X with the property such that, and here's the property you assume. You assume that mu has the additivity property, that mu of A union B always equals mu of A plus mu of B whenever the distance between the sets A and B is positive. Remember this, in a metric space, this just means the infimum of the set of distances that you get by taking the first point in A and the second point in B. See, that sounds like you'd think any reasonable, self-respecting outer measure should have that property, right? Because you're saying that the sets are separated by a positive distance. So surely it's reasonable for many measures, at least, to think that they should. Many reasonable measures surely should have the property that they're additive on those sets when they're actually separated by this fixed positive distance. Here, like this. This is a picture. This is A, this is B. Mu of A union B surely should be the same as mu of A plus mu of B, at least, unless you've got a very weird measure, you hope that might be true. And anyway, that's the hypothesis here. So assume that we've got such a measure. Then Carathéodory pointed out that whenever you have that property, it is automatically true that all Borel sets are mu measurable. Really nice theorem. Then all Borel sets are mu measurable. Provided you have this additivity property on sets that are positive distance apart from each other. And the proof is, well, once you know it's true, it's not that hard to prove, but you can say that about a lot of mathematics, actually. Realizing what's true is often really hard. Whether or not you have a proof. So let's give the proof. maybe I'll try to sketch this. So let's see, we're trying to prove that all the Borel sets are mu measurable. Now remember, the Borel sets is the smallest sigma algebra that contains all the closed sets. That's one point. Second point is the collection of mu measurable sets is a sigma algebra, right? So we want to prove in particular that all the closed sets are mu measurable. Then we'll be finished, because the collection of all measurable sets is a sigma algebra. It contains all the closed sets, so it must at least contain all the Borel sets, because the Borel sets are the smallest sigma algebra that contain all the closed sets. So we have to prove that mu S equals mu S minus C plus mu S intersection C for every S. Prove that for every closed set C contained in X, that's true. So that's what we have to prove. And so let's draw a picture of that schematic picture. It's always a bit dangerous to draw a schematic picture, but it's useful nevertheless. And let's observe that this is, let's start off with, let's look at this side. So mu S minus C, I think I'm doing that right. It's the usual thing. If you don't start these arguments off right, you get in a huge mess very quickly. But I think this is the right thing to do. Yep. There it is. Yeah. So we start off with the right-hand side there. So mu S minus C plus mu S intersects C. Okay, now I can rewrite C, here this is C. I can always rewrite C for any j equals 1, 2, etc. I can always rewrite C as Cj. This can be written as the intersection j equals 1 to infinity of Cj, where Cj is the set of x in the space, such that the distance from x to c is less than or equal to 1 over j. Now, be careful. That looks like something that you might want to state whatever the set C is, but remember that's only true because C is closed, right? If it's not closed, you can have points at zero distance from C, so this wouldn't be correct. But C is closed, so this is correct. You can take the intersection of the set of points at distance less than 1 over j. So Cj is this, so that means S minus Cj, xs minus Cj, let's look at S minus C, that's this guy here. S minus C is S minus Cj, but then I've subtracted off too much, haven't I? I've subtracted off, instead of just subtracting off C, I've subtracted off all the points at distance less than 1 over j from C. So I've got to add those back on again. Union union k equals 1 up to k equals j to infinity of rk, where rk is the stuff we have to add back on to fix this identity. So rk is the set of x in S. All the points here are in S, so we've got to stay inside S, such that the distance from x to c is bigger than 1 over k plus 1 and less than or equal to 1 over k. right, that is a correct identity, isn't it? This union is, in fact, the set of points between whose distance is between 1 over j and 0 from C. So we have correctly added that back on. So this is a correct identity. So you can write that. So that means that we can use that here. So this is equal to mu S minus Cj union k equals j to infinity, okay, plus the other term we don't touch, that's the same as it was before, mu s xc. And now this is, yes, right, right, yeah. I think that's, sorry, that's less than or equal to, right, subadditivity. Yeah, we just use subadditivity, nothing special. So this is, by subadditivity, this is less than or equal to S minus Cj plus the sum k equals j to infinity of mu rk plus mu s intersect c. By the way, remember we only actually have to do this for every s with mu s finite, because we really only have to prove the relevant inequality, right, as I mentioned before. So you only have to worry about mu s finite here. So let's assume that. It'll simplify this discussion. So we have that by subadditivity. And yes, right. And, right, S minus Cj. Okay, now here's the trick. Notice S minus C, here's Cj. The inner thing is C, but Cj is the whole thing, where this distance is 1 over j. Okay. So that's Cj. Whole thing there, like that. And notice that the S minus Cj is out here. It's out here. It's outside this bigger thing. Now notice S minus Cj has distance at least 1 over j from C. So it's one of these guys that satisfies that identity, right? So that plus mu must be additive on the union of that set and that set, because they're separated by a positive distance, you see? So this is the same as mu S minus Cj union S intersect C plus this sum still, that stays there, k equals j to infinity, mu rk. That's good. And this S minus Cj is certainly less than or equal, this is all contained in S, so this is certainly trivially less than or equal to mu of S, plus this set term. So we see what we have to do now. Remember, mu s is bigger than or equal to this by subadditivity, so we certainly less than or equal to that. So in order to prove equality, that this is equal to that, we just have to observe it's enough to know that this series is convergent. Because if this series is convergent, we're starting the sum from j to infinity, so we can just let j tend to infinity. It's the tail of a convergent series, which tends to 0, right? As j tends to infinity. So all we need to check is that this series is series of these guys, the measures of those guys, is finite. So we need the sum rk, k equals 1 to infinity, to be finite. That's all. Then we're done. Completely finished. Because we just let j tend to infinity there, and that extra term tends to 0. We get equality. So we just need that finiteness. But you see, that's actually pretty clear, because Let me make that picture a bit better. Here's C, and then RK is got distance between. It's a bit hard to draw this with too many iterations, but RK is one of these annular things here, where this distance is 1 over k plus 1, and this distance out here, a bigger distance, is 1 over k. And this is RK here. So that's RK. Now you see, RK doesn't have a positive distance from RK plus 1, notice, because RK plus 1 is exactly adjacent to it. It's the points between distance 1 over k and 1 over k minus 1. It's those points. But if you go to the next one, RK plus 2, that does have a positive distance. So you observe, this is Carathéodory's observation, that the distance between Ri and Rj is indeed positive as long as j is bigger than or equal to I plus 2. As long as you don't take two adjacent annular regions, it is a positive distance between them. So that means that if you take the sum of the even guys in particular, so sum of mu, say up to 2n, let's take the even guys, j equals 1 up to n, mu r2j, like that. So take the even indexed RKs. That indeed is additive by this assumption. Notice you can use induction on this assumption to get any finite union. It doesn't have to be just two sets. It can be any finite collection of sets as long as they're all separated by a positive distance from each other. So this can be written as mu of the union j equals 1 up to n r2j. But you see that's less than or equal to mu of s, which is finite, fixed finite number. So that proves that this series of the even indices is convergent. Of course, similarly, the sum j equals 1 to n of the odd ones, mu r2j plus 1, is also less than or equal to mu of s. So indeed, this is correct. It's finite. So that's proof of Carathéodory's theorem. Really a nice theorem. So as long as you've got this additivity property, then you do get all the Borel sets are measurable. You get that for free. That's a very nice fact. So next time I'll continue and talk about some real examples, including, well, starting with the Lebesgue measure, but of course that's not the main point here. In particular, I want to talk about Hausdorff measure and show that this can be applied to Hausdorff measure. Hausdorff measure is one of the main tools of geometric measure theory. So we're going to use these abstract theorems to talk about various properties of Hausdorff measure. So we'll stop there today.
就是礼拜一有一政府一个 room， 就是让学生讨论。那今天是 organize 的 meeting 所以有兴趣的同学就留下来一下，看你们就是说这个讨论课要怎么样进行。So we are going to have this organized meeting for this problem discussion. So today is organized meeting and problem.